And I said, surely not. So let's take a look at 17. Here it is in the beginning. And as you can see, the purple stuff, it was so easy. It was almost, you could do it in your sleep. But then I guess the problem was the particular solution, because it overlapped here, these two overlap, and you're like, well, that is not nice. And so because they overlap, you end up with this issue with trying to figure out the the values of for this. You have to throw in an extra x, and that creates this horrific nightmare of dealing with product rule of the product of three functions. So I went and I did, it wasn't too bad, was it? The first derivative, and then I went and did the second derivative, and I realized after I started doing some of this that, I left off some stuff, just a minute. I realized that a bunch of this stuff is going to cancel. I guarantee that it will cancel, and so I didn't care about it. But I do care about this piece and this piece. So those I care about. This stuff I don't care about. Don't care. If you really want me to care, I can show you the derivatives. I'll do that in Python because I don't want to have to do it by hand. But let's get this. I should probably double check my arithmetic here to make sure I've got it right. This is going to be negative, hold on a sec, negative 2 times e to the x. And this will be, wait, is that really a 4? Why did I get a 4 there? This one, just a minute. Derivative. Okay, so we've got this goes here, and then you get one of them over here. Oh, one of them from here. Okay, and then two of them from here. That's where it all came from. And then down here, we've got for sine, I've got negative 2 sines come from here. I've got, the cosine, this is whatever. Just a minute. Sorry, you got to, okay, sine, two of them. Okay, 2 sines come from here. 2 of them come from here. Okay, so it'll be negative 4. That's what it is. Okay, negative 4. We'll find out momentarily because I actually have Python fired up, ready to go. Oh, plus a bunch of other junk that I don't care about. Okay, so let's go grab Python, because why should we have to do something by hand if we can get a computer to do it for us? So let's see, is this going to do it for us? Why not? Let's see. So let's do this. Def f of x, and then just take a sec here. This is x times, or here, a times, I need to go define a. Sorry, up here. Ignore all this. This is from earlier. I just need to define a as a symbol. So a is the symbol, quote a, and b is a symbol. Symbol. And then we'll be good. Let's go down to the bottom again. Here we are. Where am I? There it is. Okay, so we have a times x times the sine of 2 times x times the expected, or e to the x. And then I have that plus b times x times the cosine of 2 times x times e to the x. And I should have just done this, return that. Return this. There we go. Okay, so what we want to do is we want to take the derivative of f of x with respect to x, and we want the second derivative. But let's just make sure this works. Apparently it doesn't. Why does it not work? Oh, I don't have the multiplication symbol. A times, let's see, now it likes it. Look at that, isn't that beautiful? And then we'll do it again, do the second derivative. So hold on a sec, print this. I don't know, everyone wants to use SymPy, right? Okay, so there it is, print that, and then we'll print the derivative. Oh, how do I know this is really, whoops, fid, if. This is really inefficient, but I don't care. That do it? Find out. Yeah, there it is. Okay, so there they are. So what did I get? Did I get it right? Did I get it right? Let's see, what matters. So here's why let's just go back here. I'm going to double check my my stuff. All I care. So there's the. If you wanted to know what the actual dot 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 was, that's what it was. But here's why I don't care about everything else. It's because I know, because of this, I know that this stuff is going to go away when you plug it in. It's just from experience, because of the fact that these solutions are like the same. When you throw an X in there and you throw it up here, the X part will go away. All you'll be left with is this part that doesn't have the X. So that's why once I got to the X's, I didn't care. So let's double check to see if I got this right. Let's see. So for the, let's see, I need the ones that don't have X in them. So the first line is the derivative. Okay, so it's a times e to the x. Okay, y prime, yes, e to the x times sine of 2x. And then b times e to the x times cosine of 2x. Yeah, those are the only ones that don't have x in them. And then for the second line is the second derivative. I have 2a e to the x sine. I'm looking right here, by the way. I'm looking for things that don't have an x as a so 2, yeah, that's, I've got that. And then 4a e to the x cosine of 2x, I've got that. And then the last two, we should have some b's. There it is, 4b e to the x sine, that's negative. Yeah, I got it. Okay, I'm happy. Okay, so I just wanted to double check. So the rest of this stuff is going to go away. So then let's, I know it's a huge, huge mess. Let's do this. So we have a times, here's what I'm going to do to make myself not have to lose my mind writing this stuff. I'm going to define this. We're going to call big F is e to the x sine of 2x, and big G is e to the x cosine of 2x. So the second derivative, so here's what I'm doing is I've got second derivative is a 2af plus 4ag plus 2bf plus minus 4, sorry, yes, I know you want to know the answer, I'm getting it for you, 4bg. Okay, so that is the, that's all that's going to matter. All of the dots aren't going to matter. So that's all that's going to matter from the second derivative. Now let's do the first derivative times 2, negative 2 times the first derivative. So minus 2 times the first derivative. Where is it? This stuff is all that I care about right here and here. So that'll be 2 times AF plus BG. And then finally, the actual function, 5 times the actual function. Notice that there are none of these in the actual function. So this is all I care about, and I want all of that to equal, oh, there it is. That's G. That equals G. Okay, so let's see if I can collect like terms. So we have 2a right here. I'm collecting the maybe the f's. Yeah, let's do the f's. 2a plus 2b minus 2a times f. Did I get that right? That surely can't be, I guess it is. And then plus 4a minus 4b minus 2b times g. Interesting. That should all equal g. So clearly this equals 0, which means that b equals 0. And then this has to equal 1. So 4a equals 1, which means a is 1/4. And so the answer for the particular solution is going to be 1/4 times, what was a? A, where's a? A times, here it is, this, e x e to the x sine of 2x. All done. Okay, so it was a nightmare, but at least I got it done. I know, it probably went so quick that some of you are like, what? But that's all right. So what else do we need to look at? So that one, I admit, was terrible. Sorry. I actually picked, you know what I did? And I think I need to be more careful. is I just was like, well, I assigned this a couple years ago. It must not be that bad. So same thing goes with tonight's homework. I might regret doing that. I don't know. It might not be that bad. We'll find out. This was admittedly, I think that if I had noticed, I'll double check. I'll double check before we leave if this stuff is terrible. So anything else from this homework that we need to look at? That was the worst? So you can set up, like, if it was something that there was no overlap, like if I had something like this, plus y is equal to e to the t, that you could do, because the general solution or the complementary solution is going to just be sine and cosine, and then the particular solution is just e to the t. So that one's easy, right? So it's not that, but it's close to that. Yeah, let's give it a try. Let's give it a try, see how that goes. Why is the heat on? I feel heat. Shouldn't be hot. It's hot outside. Here, let's give it a try. See how you do. And really all I care about is the particular solution. If you want to get the complementary solution, you can, but get the particular. That's your job, is to find a particular solution that works for these. In fact, I will put the general solution, the complementary solution, on the screen in just a sec. Here's some. You want one? Sure. Yeah, give one to Cooper in the back when it gets over there. Does everyone else get one? Okay, you've got one. You've got two. Hang on to it. I'll be there in a minute. So let me put the complementary solution, because that's easy. I know that's the easy part. So I'll do that for you. So yc is equal to c1 e to the negative 2t plus c2t. There you go. So your job is to just come up with a particular solution. So y sub p, that's your job. Get that, and you'll be in happy land. Is this one for me? Yeah. Excellent. Wait, does this mean everyone's here? 19 of you. It's wonderful. I don't need to record. Well, you can relive the magic later. Log in. Oh, you guys are done. You're just tired of. Yeah, just that. That's it. Good. Yeah. Looks pretty good to me. Uh-oh. Well, you didn't like your first answer? You changed your mind. All right. All right, take your time. But yeah, we'll come collect them in a minute. You're all set? Oh, you erased and now you're good. All right, yeah. All right. I like it. So you want is it okay? You can look.
What did Austin?
I don't know. What did Austin?
That's because I looked at it.
What? Wait. Instant F. All right, hopefully you're finishing things up. If you are done, feel free to pass that over. Remember, you just need to get the particular solution. If you insist on writing it all down, that's fine, but you don't have to. You're just still meditating? Okay, I'll come back. Back row, though. Look at that. Getting the stack. Good job. Nice, nice. Yeah, whatever. Looks okay. Close enough. Excellent. Nice. Interesting. Did you get that extra sign there? Yeah, good. I'm just kidding. There's no sign. It's a secant squared, actually. No, I'm just kidding. Sorry. Now everyone's worried. You're all set. Nice. Yeah, good. Why not? Oh, I see. You didn't box, but I see it. It's good. Here. You're just meditating. It's fine. You take your time. You take your time. Oh, you're happy now? Okay. You're reliving the magic, sort of. You can do it. All right, try to wrap things up here, and we'll collect what you have in just another minute or so. So we should try to do at least something today, since there's this groundswell of support for some sort of a alternative activity on Friday. I don't know. It's going to be a challenge for me to come up with something. Sidewalk chalk? Sidewalk chalk? We'll see. Oh, yeah. No. All right, so we're all set over here. You're looking good. You've got a box? Okay. All right, good. All right, you don't like the second one, but you like the first one. What are we at you? You like the first one as well? Yeah, you do. Good job. And you like the second one. Good job. You like them all. Ooh, I like that. See this row, we're done. Let's get her done. Oh, is that an extra? You can have it. Keep it as a souvenir. Yeah, you're still meditating. Yeah, you're good enough. Do you have a number? You have something. All right, now you've got, I think you're the holdout. All right, very nice. Sines and cosines, good job. Anyone else? Okay. Oh, you've got one. Okay, sorry. Good job. Okay. Let's shove it in here. Anything else? Okay. Okay, let's see what I got. Hopefully I got it right. Here we go. So so first one is this thing, and I said, okay, particular solution should be some linear polynomial. At plus b sounds good. And so the derivative is a, and I didn't even bother with the second derivative because it's 0. And then I shoved these over into there, and I got this expression. So 4 times the derivative plus 4 times the function should equal t. And then collect like terms. Notice that this is the only thing with t in it. And so that means that 4a should equal 1, which means a is 1/4. And then 4a, I should have written these down, 4a equals 1 from the t's, and then 4a plus 4b should equal 0 because there's no constants over there. So there it is. There's the particular solution. And if you folded it in with the general solution or the complementary solution, then you're doing great. So I saw a lot of 1/4. Good job. You might have had a plus instead of a minus there, but that's probably just because you did some algebra wrong. Okay, this one, e to the 3t. So it's just e to the 3t. There's nothing else here. And it doesn't intersect with any of this mess over here. So that's it. You got e to the 3t. So that's the only thing you have for your particular solution is a e to the 3t. Did the derivative, second derivative. I shoved them all into here, and I got that. Well, I guess I kind of skipped a step. Here, I'll write it down. 25a e to the 3t is equal to e to, does that make you feel better? And then that gave me this, and that gave me this, and so there's the particular solution there. So some of you wanted to make that into 25, I don't know. Okay. Go, 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 go. Okay, so let's take a look at this. Y double prime plus y prime is equal to secant squared. I know, you thought that the homework was bad. Take a look at that. Okay, oh wait, I'm sorry, this is supposed to be just a y. Okay, so what's the big deal here, right? I mean, the complementary solution, not a problem at all, because you probably can do it in your head, but just in case, take a sec and see if you can get that complementary solution. C1 and C2 times, what are the two fundamental solutions to this particular differential equation? So take a minute, see if you can work it out. And then we'll talk about that secant squared. Oh, I could just pick someone out of the blue, couldn't I? Let's do that. All right, Asal, do you get a complementary solution for this? Or do you know what the building blocks are? Yeah, r squared plus 1 equals 0. Very good. So I'll put that down. So r squared plus 1 equals 0. You're going to do that to figure out what this complementary solution is. Let me solve that for you. You get r squared is equal to -1, which means that r is plus or minus I. So this plus or minus I, that should trigger something in your head like, oh yeah, that's right, something weird happened. So very nice. So Rachel J, what are the two fundamental solutions using Asal's solution there? Yeah, sine and cosine. So you're like, well, anytime you have complex numbers, you're going to have sines and cosines. It's a nightmare. And so here we are, sine of x and cosine of x. Very nice. Now, so that's not the problem with this, is it? The problem is right there. What is that doing there? Well, let's see if we can work it out. If we were going to go with what we've learned so far, this so-called method of undetermined coefficients, you would say, okay, I need to come up with a particular solution. And that particular solution should have secant squared in it. but it should also have the derivative of secant squared, which is tangent, 2 secant tangent, secant squared tangent. Is that what it, sorry, I should have actually done this. Here, just a minute. What's the derivative of secant squared? I keep wanting to put a theta there. So it's 2 secant times the derivative of secant, which is secant tangent. Okay. So we have to have that. But then once you have that, you have to have the derivative of that as well. That's the way this rolls, is you have this thing plus all of its derivatives. So where do we stop? We never stop. This thing goes on forever. If you keep going, you get more and more secants and tangents because of the fact that the derivative of tangent is secant squared. You're going to have something like this, secant to the fourth. This is, I keep putting thetas in here. Sorry, these are all x's. And then you're also going to probably need a secant cubed tangent and who knows what else. So yeah, it just gets worse and worse as you go along. So this is no good. No, I refuse. So there must be a better way, and that's what today's all about, is coming up with a better way of solving differential equations like this. By the way, here's another one, just so here, I'll just use the same basic start. Y double prime plus y is 1 over x. Imagine what you're going to do with this. What does the particular solution look like? The particular solution is going to be x to the negative first plus the derivative of x to the negative first is x. Well, hey, when do we stop this madness? We never do, right? It goes on forever. So that's no good. You can't do this. So whenever you have a forcing function that forces you to have an infinite number of, where did my PowerPoint go? An infinite number of like derivatives, then you got to come up with a different way. So the other way that we're going to use is called the variation of parameters, and variation of parameters is just a way of coming up with a particular solution without going through all of the business of trying to guess all the derivatives. Now, unfortunately, the theory behind this is a little bit complicated. So let me just, I'm not going to do all of the details, but I want to remind you of something. Okay, we'll do it. And that's this, linear first order differential equations. This is where we get the idea for coming up with variation of parameters. So this is just a reminder, is that if you have a differential equation that looks like this, you come up with an integrating factor. The integrating factor looks something like this, e to the integral of p of x dx. And what's going to happen is you take that, whatever that is, and you multiply it through here. And then after doing a little bit of work, I guess I've skipped a whole bunch of steps, haven't I? So here, I'll put those in there. You have this e to the integral of p of x dx times this stuff times e to the integral of p of x dx. So you've got all of this stuff. And then you're going to integrate both sides. The left side, here, I'm going to erase this over here. Yeah, you probably don't, well, here, I'm going to do it anyway, because I care as a mathematician. So on the left side, because you're using the product rule, or you're reversing the product rule, you know that that's going to be e to the integral of p of x dx times y. On the left side. On the right side, you're going to have the integral of f of x times e to the integral of p of x dx, whatever that is. So that this thing was your integrating factor, and it just ends up, that's the way it kind of ends up every single time. And then when you're solving for this, once you've got this figured out, you end up dividing both sides by this thing to get your y. And that gives you this nightmare. But don't fret, because if you didn't have f of x there, whoops, where did it go? Where did it go? There it is. If the f of x was gone, so this here, in a sense, is a non-homogeneous differential equation. But if this was 0, and the p of x is a problem, but we're going to ignore it for a minute. and we're going to treat this as if it were a homogeneous differential equation, you could do the same thing, and the solution would be a lot simpler. You wouldn't have this nasty thing here. So you would just have this. So you'll notice that this is like your complementary solution, and this stuff here is the particular solution. So the complementary solution is this thing. The particular solution is this times an integral. So I point that out because the method of variation of parameters is similar to this. So just to illustrate this, you could, with something like this, you could do this in 2 stages instead of the way we've been used to doing it. So let me show you the 2 stages. First of all, start off, so this is linear, by the way. And so we're used to doing this using an integrating factor. So you could do it this way by, first of all, starting off like this, and then solving this. And the way you solve this is you just say that y is equal to c times e to the integral of 4 over t dt. I'm sorry, the negative of that. So that should be a negative there. Sorry about that. So let's actually do this. Not hard. It's not a hard one to do. So let's see. This is y is equal to c times e to the negative natural log of, 4 times natural log of t. Isn't that what we get? And so that's going to be y is equal to c times e to the natural log of t to the negative 4. So y is ct to the negative 4. And that we're going to call the complementary solution. So that is the solution to this differential equation. So just to, and I know I've kind of gone this really quickly, but that comes from the fact that if you think of this as a linear differential equation here, the solution is actually really easy because you're just doing the integrating factor. That's all you need to do. You don't have to worry about this thing right here. So that's your first step. Then your second step is to recognize that once you have that, it's the same as this, and then we have to do a little bit of work here, which is going to be annoying, but we can do this. So let's do the little bit of work over here. So I'm going to draw a line, and then in black, I'll come up with the particular solution. The particular solution is going to be this thing, t to the negative 4, times the integral of t to the negative 4 times 1 over t cubed dt. Let me just go back here so you can see what this is. Oh, I'm sorry, that should be a positive here. So you have that. This comes from your complementary solution, and then you multiply it by this integral. And this is all what you would have done if you, so here, this should be a plus here. So the particular solution is t to the negative 4 times the integral of t dt. Sorry, it's a bit of a mess there. So I've just combined those two things. And then that gives me t to the negative 4 times t squared over 2 plus c, but let's ignore that for now because we just need a particular solution. So the particular solution is going to be t to the negative 2 over 2. So what this tells me is that the general solution to this differential equation will be the sum of those two things if you add them up. So I know I kind of blew through that really quickly, but it's exactly the same thing you would have gotten if you had gone through the linear technique. So what we're going to do is we're going to adapt this to work for more complicated second order differential equations. So it's the same idea. So let's just cut to the end here because you probably don't care about, well, yeah, I shouldn't say that. It feels so bad. Okay, let's skip over that and go to this. Okay. So variation of parameters. So here's how this is going to work. You have a linear second order differential equation that looks something like this. Sorry, this should be an F. I thought I fixed that. Apparently I didn't. So you have some sort of a differential equation, and what you're going to do is you're going to end up with something, oh, now it's F, sorry. So you're going to have some sort of differential equation that looks like this, And we're going to solve this in 2 stages. We'll first of all solve the homogeneous part, which is the stuff where this is 0. So change f of x to 0. And then after you solve that, so you have this differential equation, so you solve the complementary solution. That's just this part, just like what we did before. So that's not changing. But then after you do that, to find the particular part, this is going to look sort of similar to what I did back there with the linear differential equation. I know this is really scary, but you're going to compute all of these determinants, to which we never went over the details, but basically what this is this is getting all of this stuff, thinking of this as a linear differential equation, putting it all together and getting this sort of solution sort of the roundabout way. But what I wanted to point out here is that the particular solution looks similar. So we have these things, and those things are similar to back here where I took the complementary solution right there and multiplied it by an integral. So you've got the complementary solution times an integral in each case. Let me walk you through. This is, I think it's probably easier if we actually do it slowly, because this is, how can you digest all that? Let's go ahead and just do it with a simple example. So this is a simple example that hopefully will help illustrate the method. So first off, you're going to start by getting the complementary solution. So that's step 1. You know what? I can't deal with the PowerPoint. Let's do this on Notability. Hold on a sec. So you can do this yourself, though. This is easy. So the first step. In fact, you could do the whole thing using the old method. So this is, why is that up there? Just a minute. Paste it down here. That's better. So so step 1, I'll make steps. Step 1 is solve this. So take a minute, get your solution. I'll pick a rando, and we'll get it done. See, we're doing great. All right, so Haven, what's the first step to solving this blue equation? Ignore the 2t for a minute. What did you do? Oh, I love it. R squared plus R equals 0. Perfect. Getting started. So you probably were going to want me to factor this, because I know that's a hard one to factor. So there it is. And then we're going to solve that. So we got R equals 0 and R equals -1. So there we go. R equals 0, R equals -1. Caden, what are we going to do with that R equals 0 and R equals -1? Okay, so C1 e to the 0 plus C2 e to the negative, is this t or x? T. So -t. So something like this. So I probably would want to just do this. C1 plus C2 e to the -t. How's that? So that's your first move. Just like what you did for today's quiz, just like what you did for last night's homework, you're going to find a complementary solution. Now the variation of parameters. So to do the variation of parameters, and I should point out that for this one, you could have done this using, you probably would prefer using the methods that we used for today's homework with this, just because it's way easier in this case. But let's use variation of parameters to see how it works. So variation of parameters, what you're going to do is you're going to start by labeling. Let me pick a different color than that. Let's see what colors. I'll use red. So you start by labeling the the fundamental solutions. Y1 is the first fundamental solution, which is just a constant, right? So I'll just call it 1. And Y2 is the other fundamental solution, which is e to the -t. So that's step 1. Step 2 is we're going to compute this Wronskian determinant, but it's just with 2 functions, so it's not a big deal. So this Wronskian, we had it before. It's just a matrix made up of these functions and their derivatives. So I have those two functions and then all of their derivatives. Well, in this case, because there's two functions, I will have two derivatives. And this is just, you remember, this is the test to see if you have linearly independent functions. So that's all this is. So let's go ahead. Adric, what's the derivative of 1?
Yeah.
Okay, very good. And then Mariah, what's the derivative of e to the negative t? Very nice. So negative e to the negative t. Since this is a 2 by 2 matrix, I'm not going to bother with doing anything complicated. Just multiply these out, and I get negative e to the negative t minus 0 e to the negative t, which is equal to negative e to the negative t. So that's step 2. So maybe I should label these. Step 2 is get this Wronskian. This is challenging. This is quite a complicated procedure. Just so you know, it's going to take a little while to get used to it. In fact, I think that the little while it's going to take will include whatever we do on Friday. So, because I can see that we only have 10 minutes now, and there's no way I'm going to make you do the homework I've planned for Friday. So maybe I can pick one. Yeah, if you give me some time after class, I'll pick one that's super easy for you to do for Friday, maybe. Okay, so there's number 2. Number 3 is we have to compute, whoops, let's see, I gotta put a circle around that. Number 3, I need a new color. Give me a sec here. How about this? Why aren't there any good colors? How about that color? Okay, so number 3, what we're gonna do is we're gonna get u1 prime and u2 prime. So u1 prime is going to equal the determinant. No, never mind. U1 prime, let's just do it this way. It's going to be the function times y2. Did I label these? Oh, I did. They're up there. Oh, the negative. Sorry, this is a determinant, but here, I can put the determinant up there, but you don't, it's much easier if we think of it in terms of, here it is. So it's this determinant right here, but it's always going to end up being negative y2 times the function value. So let's not bother with the determinant. Let's just cut right to that negative y2 times the function. So let's see, here it is. And then we're going to divide this by the Wronskian, which is this number right here, or that expression. So this is going to be negative, where was my function, 2t? Negative 2t times y2, that's e to the negative t, all over the Wronskian, which is negative e to the negative t. And this is convenient because these cancel, and you're left with 2t. Now notice that that's u1 prime, and so I'll bet you can tell me what u1 is without too much effort. So let me find someone. Cooper C, what's u1 if u1 prime is just 2t? Yeah, t squared. Very good. So there's t squared. Now we're going to do the same thing to compute u2, the other piece for this particular solution. So u2 prime is going to be f of x times y1 over the Wronskian. You might say, well, why is this negative and this one positive? Okay, I'll show you, but it'll just cost you in the sense that we have to look at these matrices again. You can see that with this matrix, the part that ends up being non-zero is this down diagonal, so positive y1 times f, whereas this one, it's negative because it's the up diagonal. So that's why, but here we'll go back here. So let's go ahead and compute this. This one will be, let's see, the function is 2t. So we have 2t times 1 over negative e to the negative t. This one is not as happy. Sorry, that should be a negative. So there's u2 prime. So u2 is going to be the integral of that. Let's see if we can do this. Negative 2 times t e to the t minus e to the t. Does that work? I know you would use integration by parts. I'm just taking a guess and then checking. Honestly, that's all I did. And it's okay because this is easy. Double check. Derivative of this is that, isn't it? Things cancel? No one's saying yes. Okay, I'll do it. I'll do it. T e to the t minus e to the t. Let's do the derivative. Is going to be negative 2 times t e to the t plus e to the t minus e to the t. And sure enough, e to the t. Check. Happy face. Okay, so yeah, so it's, I mean, you could do integration by parts if you want to, but we've done this so many times, you probably aren't going to be too surprised by that. Okay, so final step, that's number 3. Number 4, final step is that the particular solution is going to be u1 times y1 plus u2 times y2. I know, why does it have to be so complicated? Well, it's variation of parameters. And so this particular solution ends up being, let's see, u1, that's t squared. Whoa, come on back here. T squared times y1. Y1 was just 1, okay? T squared times 1 plus u2, that's that mess there. How about if I write it this way? Negative 2t plus 2 times e to the t times, that's this thing. I just combined some things and factored out the e to the t, times this, e to the negative t. So the particular solution is t squared minus 2t plus 2. Now, I just got to point out that this was really dumb to do it this way. Why? Why would I do it? Look how much work that was. When I could have just done it the way we did it for class today, and I could have said, hey, my particular solution is going to be a times t squared plus b times t plus c. You might say, why is there an a times t squared when this is just a t? The reason is because of this, is it overlaps with this. So notice that the C1 for the general solution, and you have a C in, that's the derivative of t. So that's why I had to throw an extra t in there. That's the price I pay. But I could have done this, and I would have gotten down to this eventually. Wouldn't have been that hard. But what the power of this is that now we'll have a way of dealing with this. Where'd it go? Where'd it go? There it is. Yes, that one. So unfortunately, we don't have enough time to do this right now, but we will have time to do this on Friday, I'm sure, possibly with Sidewalk Chalk. I don't know. I'll see. I will seriously consider it. I don't know if I can handle it. We'll see. Okay, I'm going to stop the recording, and then we'll, if you want to come chat, you can. Don't forget to stop and see